All right, let's dive into a question that sounds really simple but honestly trips almost everybody up. What's the actual difference between heat and temperature? And to get our heads around it, we're going to start with a little puzzle you've probably felt for yourself. So picture this. You're outside, it's a cool day, you see a metal park bench and a wooden one right next to it. You touch them both, and that metal bench feels so much colder, right? But here's the kicker. If you took out a thermometer, it would tell you they are the exact same temperature. So what in the world is going on? It's not magic, it's physics. And the answer is all wrapped up in the difference between these two ideas. Okay, so to crack that bench mystery, we have to start with the basics. First things first, what even is temperature? We usually just think of temperature as, a number on the weather app. But what it really is, scientifically, is a measure of motion on a microscopic scale. And that phrase right there is the key to everything. Average kinetic energy. Yeah, that's literally it. Just imagine that everything around you is made of trillions of tiny particles, all buzzing and vibrating. In something hot, like a fresh cup of coffee, those particles are going absolutely wild, zipping around like crazy. But in an ice cube, they're moving much, much slower, kind of just shivering in place. Temperature is just our way of measuring the average speed of that microscopic dance. So if temperature is all about these invisible molecules bouncing around, how in the world do we actually put a number on it? Well, with thermometers, of course. And what's brilliant is how we create the scales they use. Whether you're talking Celsius, Fahrenheit, or Kelvin, they all work by picking two fixed, totally reliable points in nature. The freezing and boiling points of water are the classic ones, and then just dividing up the space in between into equal units, or degrees. And the only reason a thermometer works at all is because of this really fundamental rule of the universe called the zeroth law of thermodynamics. It sounds super intimidating, but the idea is actually simple. It just says that if you stick a thermometer in a cup of water and it reads 20 degrees, and then you put that same thermometer against a block of wood and it also reads 20 degrees, then the water and the wood have to be the same temperature. The thermometer is just the reliable middleman. Okay, so I think we've got a good grip on temperature now, so let's bring in its partner in crime, heat. And the number one thing you need to remember about heat is that it is all about movement. So this is the absolute crucial point. Heat is not something an object has. It's not a property. Heat is energy in transit. It's the flow of energy that only happens when there's a difference in temperature between two things. If there's no temperature difference, there's no heat flow. Period. Let's put these two side by side, because this is really the heart of it. Temperature is a measure of the average energy of molecules. That's why a tiny cup of boiling water and a huge bathtub full of boiling water can have the same temperature, 100 degrees Celsius. But that bathtub has way, way more total thermal energy, right? Because it has so many more molecules. And this is a huge deal because heat is the transfer of that energy. The bathtub has a much, much greater ability to transfer heat than the little cup does. So now that we know heat is energy on the move, let's talk about how it actually gets from point A to point B. And the first way is something called conduction. Conduction is basically heat transfer by touch. It happens when things are in direct contact. And the key part here is that the object itself doesn't move. The energy just gets passed through it. The best way to think about it is like a line of dominoes. The hot end is where you flick that first domino. That jiggling molecule bumps into its neighbor, passing on some energy. That neighbor then bumps into its neighbor, and so on and so on. It's a chain reaction of collisions that sends a wave of energy right through the material. And boom, this brings us right back to our bench. Your hand is warmer than both the metal and the wooden benches. So when you touch them, heat immediately starts to flow from your hand into the bench. Now, metal is a fantastic conductor. It yanks that heat away from your hand super fast. And that rapid loss of energy is what your nerves actually feel and register as cold. Wood, on the other hand, is a poor conductor. It's an insulator. It transfers the heat away much more slowly. It isn't robbing your hand of warmth as quickly, so it feels warmer to the touch. It's the exact same reason a tile floor feels colder on your bare feet than a rug does, even though they're both at the same room temperature. Mystery solved. All right, let's move on to the next method of heat travel. Our second type is convection. So remember how with conduction the material stays put? Well, convection is the opposite. It's all about the material itself physically moving around. And this happens in fluids, which in physics just means liquids and gases. The classic example here is a pot of water on the stove. The burner heats the bottom of the pot, and that heat conducts into the water at the very bottom. As that water gets hot, it expands, becomes less dense, and starts to rise up to the top. Meanwhile, the cooler, denser water from the top sinks down to take its place, where it gets heated and rises. This creates this constant rolling circular flow called a convection current, and that's what distributes the heat through the whole pot. This is also what creates wind and ocean currents. And that brings us to our third and final method, radiation. And let me tell you, this one is in a league of its own. Okay, this slide says it all. This is the huge, fundamental difference that sets radiation apart. Conduction and convection, they both need stuff. They need a medium, atoms and molecules to pass the energy along. Radiation, it's totally different. It needs no medium at all. It can travel through the total, complete emptiness of space. So get this. Anything and everything that has a temperature above absolute zero is constantly giving off thermal radiation as electromagnetic waves. The hotter something is, the more energy it radiates. This is how you can feel the warmth of a campfire from across the yard without touching it. And, most incredibly, it's how the heat from the sun gets to us across 93 million miles of empty space. So we have covered a ton of ground here. Let's boil it all down to the one single idea that you really need to take away from all this. If you remember just one thing from this entire explainer, please make it this right here. Temperature is a property. It's something an object has. It's a measurement of its internal energy. Heat, on the other hand, is an action. It's something an object does. It's the process of transferring that energy. An object cannot contain heat, but it can transfer it. And that leaves us with one last little question to chew on. We've defined heat as the transfer of thermal energy. So what does that make cold? Is cold a real thing? Or is feeling cold just what it feels like to have heat rapidly leaving your body? Is cold simply the absence of heat? Something to think about. Thanks for tuning in.